So good morning to everybody in Toronto. I'm still in the United States. This is the second part of the lecture I studied yesterday. And thanks Bob for the invitation, for the introduction. This is the second part of the lecture I started yesterday, and so I have basically two things I like to do in this lecture. I'm going to talk about a problem I'm going to talk about some work with some on the long-term regularity of gravity capillary waterways, which is a very difficult model. I'm going to remind exactly what these problems were, and I'm going to state theorems precisely. So the first goal is to go through some of the ideas that allowed us to prove global regularity for gravity capillary waterways in 3 dimensions. That's number one, and that's a theorem that's been published a couple of years ago. And my second goal is to talk about some recent work, what is a very interesting project, I think very difficult, very far, but the kind of but an interesting project that has to do with establishing what's called the wave kinetic equation for waterways, or more realistically understanding the concept of wave turbulence for the rotational waterway system. It's not hydrodynamic turbulence, so it's not the same as turbulence for Euler or for Navier-Stokes, but it's turbulence for wave equation. So that's called wave turbulence, and there is some direction in which one could understand. This is what I think is the ultimate problem as far as long-term regularity of waterways. So now to get started, here I'm going through some of the slides that I had yesterday, just to go again to the notation to remind people of what we are doing. So looking at the rotational waterways. So we are in a specialized setting in which we are thinking only of the rotational waterways. And if the interface is a graph, then we can reduce the entire equation to the only two real valued functions that evolve. So the entire dynamics of the system is captured by two real valued functions. The two real valued functions are h, which is the height of the interface. We're going to work all the time in Eulerian coordinates. So we are thinking the domain lives under this function h, which is the height of the interface, and which changes in time. And then the second function parameterizes the evolution is the function little phi, which is the restriction of the velocity potential. So because I think of rotational waterways, we can think that the velocity v is given by the gradient of capital phi. So that's the velocity potential. So capital phi is the velocity potential. Coming from the fact that it's incompressible, this means that the Laplacian of phi is equal to 0. And then we restrict, so we take this velocity potential, we restrict to the interface. So these are the two variables that capture the entire evolution. And the system, so the system which I talked about yesterday, which is the system 1 that we are going to use, it says that dth, so it's an evolution system for h and phi. dth is gh phi, where gh is the certain renormalization of the Dirichlet-Neumann map associated domain omega t. So dth is gh phi, and dt phi is minus gh. This is one term. This is one term, plus sigma times some kind of perturbation of the Laplacian of h. So this would be sigma delta h, except for the denominator, plus quadratic terms that come from the quadratic terms in the Euler equation. So this is minus 1/2 grad phi squared, and it's another component of the velocity squared, and there are some other corrections to that. So this is the system for these two variables, and this gives so these two variables, they capture the entire evolution of the entire evolution of the problem. Now, I said this yesterday, but I should say it again. This is a good system as long it's good for certain purposes. It's good, for example, first of all, it's restricted to rotational waterways. But in that case, it's good to understand, for example, local regularity. And I mentioned yesterday briefly some results of Alazar-Burjuli on the local regularity. It's also good to understand the global regularity, so the long-term regularity, the global regularity. It's also good to understand sometimes like certain Stokes waves, so for example, some specific solitons, it's good to understand them in this kind of coordinates, but it's not good for everything. So for example, if you want to talk about overturning of the interface, or if you want to talk about splash singularities, there's not a good this system of coordinates is not good because it won't allow. This is predicated, the whole construction is predicated on the fact that H is a graph above the bottom. So, but it's good for the purpose for the purposes that we are looking. We are for the purpose of this lecture. And this system is called the Zakharov-Kreishan-Sulem formulation of the water wave, the rotational water wave equation, and that meets an exact conserved energy, a Hamiltonian, which has the form of GH phi times phi plus some component coming from the gravity G over 2H squared plus some component coming from the surface tension sigma nabla H squared with some nonlinear correction of sigma nabla H squared. So this is the sum of the kinetic energy and the potential energies. So now I'm going to state the theorem that we are going to prove in the first part today. So this is theorem with this is a theorem. So you're looking at the system. This is the system 1 here. So this is the system 1. DTH is GH phi. And they're looking at the gravity capillary system, which means that we set both G and sigma non-zero. In terms of that they are both non-zero, we can rescale them to make them both 1. I'm going to talk about work with Yu Deng, Benoit Poussader, and Fabio Poussader. This is work of a couple that we published a few years ago, like 2 or 3 years ago, on the global regularity of this system. And so Yu Deng, they all at the time were all in Princeton. Now everybody else has moved. So Yu Deng is now at USC. Benoit Poussader is at Brown, and Fabio Poussader is, as you know, in Toronto. So the theorem that we have is the following. We are looking at small initial data, U naught, and U naught, like just like we had for gravity waterways yesterday, U naught is a certain combination of H and phi. This is the combination that diagonalizes the linear part, and the combination is 1 minus delta 1 minus delta power 1/2 times H plus I nabla to the 1/2 times phi. So this is the combination that's needed in order to diagonalize the linear part of the system. And we are looking at data U naught, which is assumed to be small. And it's assumed to be small in a large Sobolev norm, Hn 0. And also it's assumed to be small relative to certain rotations. It turns out that given that we are in 2 dimensions, there are some vector fields that commute to the linear part of the system. Actually, the only vector field that commutes to the linear part of the system is the rotation vector field x1 d2 minus x2 d1. So I'm going to take rotations in the variables x, and they are looking at initial data that's small relative to Sobolev derivatives and relative to this vector so it's small relative to the rotation vector field omega. You should think that n0 is very big, is like 4,000, and n1 is also big, is about 2,000. So the number of derivatives on the vector field is about half as many as the number of derivatives on the Sobolev derivatives. So you're assuming that this norm is small, and there's one more norm that I'm going to describe later. It's consistent with the method that I talked about yesterday, the Zenor method, which is a certain special norm of the function. You're going to see, here it's too complicated to write down the Z norm exactly on this slide, but you're going to see it's some kind of description of the function around certain frequency. It's basically a description, a more special description at low frequencies of the initial data. At high frequencies, is the energy norm that matters the most, is the strongest norm, but at middle frequency, like a size 1, is the Zenor method that captures the initial data. Okay, so looking at small data of this type, and the Z norm is going to, I'm going to have the Z norm later on. And actually also wanted to, when defining the Z norm, I wanted to address the question, because here it's easier to see the question that Catherine asked yesterday about how do you define a Z norm? So how do you think of what to put in the Z norm? So it's going to be pretty clear when I will describe it later on how that gets defined. And so this is the initial, so we start with small initial data, and the conclusion is there is a global solution, and I write it again in this form, in this complex form, I minus 1 minus delta to the 1/2 h plus I nabla to the 1/2 phi, which is going to stay smooth of this system, and which does the following: the energies. It's a similar situation as we had last time. All the energies, all the high order energies, they grow slowly in delta. The Z-norm stays bounded, and one has decay. One has a certain rate of decay of the solution U of t. It turns out that the optimal rate of decay is t to the power minus 5/6. So that's, we almost get the optimal rate of decay of the solution in L infinity. So this is the conclusion that we get about the solution. That we have a solution, the energy grows, but we continue to control the Z norm, and we control the Z norm implies that the solution has a certain decay. Now lambda, so the factor lambda that has to do with the linear dispersion is in this case square root of nabla plus nabla cubed. And how do we get, so how do we do the linearization first? The linearization, if we just look at, if we linearize around h is equal to 0 and phi is equal to 0, then the two equations, this was dth is gh phi, and gh phi is absolute value of nabla phi at the linear level, and dt phi is minus h plus delta h. And then if we define the complex variable in this way, 1 minus delta to the 1/2, the same as on the previous slide, 1 minus delta to the power 1/2 times the linear part of 1 minus delta power 1/2 times h plus I nabla to the 1/2 times phi. Then we can define the complex variable in this way. We'll diagonalize the system, and we will get at the linear level, we get the dispersive equation dt u, so u is this variable, plus I lambda u is equal to 0, where lambda this time becomes square root of nabla plus nabla cube. So this would have been, if you want to think in the general case, it would have been square root of g times absolute value of nabla plus sigma times absolute value of nabla cube. Then we are assuming that g and sigma, they are both equal to 1. So that's what leads to absolute value of nabla plus absolute value of nabla cube. What we had yesterday, so in the gravity case, so this would have been square root of g times absolute value of nabla plus sigma, but sigma is equal to 0, so that would have been just square root of g times absolute value of nabla. But now we're looking at the gravity capillary system. And just like yesterday, because I want to talk about the ideas that lead to global regularity. Just like yesterday, I'm going to assume that actually I'm going to look at a simplified system. We're not going to think of the full waterway system, which is too complicated. It's not transparent. So you get too many things going on at the same time, including the fact that the local theory was hard to begin with. And there are just too many things that are going on at the same time. So we know by now that the local theory can be done. But there are other issues that we need to understand as far as the global theory. So I'm going to talk just to be able to present all of these ideas in a simpler setting. I'm going to talk about a simplified model. So a simplified model works. It's about the same as last time. We look at dtu plus I lambda u, and the nonlinearity, I just make it a very simpler quadratic nonlinearity. So it's grad v times grad u plus 1/2 delta v times u. So u is complex valued, and v is defined in this way. Look at the frequency of size 1, frequency between 2 to the minus 10 and 2 to the 10. So this is what this projection is. And it's important to make it real value. So it's the real part of u. So we can think of this as being some kind of a version of the water wave system. And it turns out that for the global analysis, what we've been able to do is to analyze the system, and everything that we've been able to do to say about the system, we're able to eventually translate to the full problem. Assuming, of course, you have to do the energy estimates, accounting for the fact that even the local theory is hard, while for this system, the local theory is not hard. So that's that's one thing to keep in mind. But other than the local theory and other than the issues that are addressed at the level of the local theory, understanding the global behavior for this system, understanding how the decay works, and understanding what happens asymptotically in time has the same level of difficulty as the original system. Now, as I said, V is real valued, and it's arranged, the nonlinearity is arranged, so I arranged you grad V, grad U plus 1/2 delta VU, arranged in such a way as to have an exact L2 conservation law. Okay, something happened. So I arranged to have an exact L2 conservation law, which is going to be important. And we can think that in the original problem, there was a Hamiltonian. So as long as we're able to track the fact that the Hamiltonian is conserved, we have this ingredient in the original problem as well. So there's a Hamiltonian which is at the level of the L2 norm of U, which is conserved in the original problem. So this is the logic for this model. It captures. It's simpler than the real problem, but this does capture. It's going to capture the issues that we need to address in the global regularity result. And now these are a couple of the slides that I had yesterday, just because maybe some people were not here yesterday. So we use what we call the Zenor method, which means that we want to do the following. It's a bootstrap argument, but it's a special kind of bootstrap argument in which we want to propagate control. We want to propagate control of the energy functionals, and the energy functions, we apply the vector fields to the solution U of t, and we allow all of them to grow. Now here's a mistake. This W should have been powers of omega. I just took the slide from yesterday, and yesterday we had a scaling vector field for the gravity waterway system, for the gravity capillary system. We have the powers of omega. So W's are either Sobolev derivatives or powers of omega. So instead of S here, this part of this is a mistake. It should have been omega. So that's one part that we bootstrap. So we bootstrap high order energies, and we allow them all to grow with various hierarchies. So there's a hierarchy here we can have that every vector field is a different rate of growth, and we have we want to bootstrap the Zenor. So the Zenor, which we haven't defined yet, because I wanted to get to the question of how we define a Zenor. So the Z-norm, we assume that is smaller than a constant epsilon1, and we assume that at time t is equal to 0, both the Z-norm and this energy norm, they are smaller than a smaller constant epsilon0, where epsilon0 is the size of epsilon1. It's much more than epsilon1. It's epsilon1 to the power 3/2. So this is the assumptions that we make. And then to close the theorem, we need to prove the improved bootstrap estimate. So you need to prove that that we have the same energy control, but with the better constant epsilon0 instead of the constant epsilon1 that we assumed. And we have to assume that we have the same Zenor control, again with the better constant epsilon0 instead of the constant epsilon1 we assumed. So that's the this is how the bootstrap works. Now the Zenor, like I said, the Zenor is extremely important. It balances. This has been one can think of this if you have lots of vector fields, then you might not need any Zenor, and that's already that would be what's known as the vector fields method. That goes back to the working Gates of Kleinerman and Christodoulou and many others. So if you have a lot of vector fields in the problem, you might be able to understand the problem completely using vector fields, and that would be that would mean that there is no Zenor. The Zenor would be weak. At the other end, if you were in a semi-linear problem, you wouldn't need to prove the energy separate. Like for example, if one is thinking of the cubic NLS, the Zenor could be, for example, a Strickard's norm, and that will already capture the energy. One would not need to have the energy done separately. So these are the two ends where either the Zenor could be very strong or the Zenor could be very weak relative to the energy. But what's important for us here is to have the flexibility to arrange the Zenor relative to. So it's important to be able to arrange to have the flexibility to choose the Zenor. And the implementation level, like I said yesterday, I would like to use all the vector fields that commute to the linearized equation. And the key is to find a Z-norm that allows for the that cooperates with these vector fields. All right, so these were the two slides that I had yesterday, just to describe the abstract level how the method works. Now let's look at our problem. So in our problem, we want to control energies first. So this is the slide. I want to control energies, and we define W to be the energy, and we take the d by dt of the energy, and we get a quantity of this form, W times W times this is coming from the nonlinearity, the real part of U xc minus eta, and we write the symbol. Now, because I arranged the nonlinearity to have DL2 conservation, it turns out that this symbol, you see, when n is equal to 0, then the symbol is 0. But in general, the symbol has this decomposition, which we have this factor, which turns out to be a very, very valuable factor. It turns out to be what they call a depletion factor, so it's small. And we have a factor that's of size 1. So now we are looking to, so the increment of the energy is given by this cubic expression, the form W times W times the real part of U. And you are looking to control, to understand the increment of the energy, we need to understand the space-time integrals. So here, this is the integral at some time t, but we need to understand the integral at all. So we need to understand the integral over time. And as I said, this depletion factor is going to turn out to be important at some point. It's correlated to the fact that there are resonances in the problem, but it somehow it weakens the contribution of the resonances. Now, there are two key differences that make the problem a lot harder than, for example, the gravity one, either the gravity or the surface tension system. Both the gravity and the surface tension systems were proved, there was global regularity proved by Germain, Masmoudi, and Chatat for both of them. And in the gravity case, there was the work of C.J. Wu, who proved also global regularity. However, there is one issue that's, there are two issues, the combination of two issues that make the gravity capillary problem a lot harder. Now, the first one is that the dispersion relation that we had, the dispersion relation C plus square root of C plus C cubed, has stationary points. And it has an entire circle of stationary points that comes, so here we have the graph of the, so this is the dispersion relation lambda r is square root of r plus r cubed. This is the graph of lambda of r. When we take the derivative, we get lambda prime of r, which is this curve. And it turns out that this is a stationary point. So there is a point where the lambda prime is equal to 0. And because we are in 2 dimensions, that point decreased. So this is a stationary point. And because we are in 2 dimensions, as a result, the linear solutions can only have much slower pointwise decay. They cannot have 1 over t pointwise decay. The best they can have is 1 over t to the power 5 over 6 pointwise decay. Even for the Schwarz function that you plug the Schwarz function in, and it turns out that it's not possible to have better than t to the minus 5 over 6 pointwise decay. This is different. If one were to have 1 over t decay, then one would be able to close the energy estimates. And now there's one more line here that's not being used, this line gamma 1 that corresponds to square root of 2. So the frequency gamma 1 is square root of 2. It's going to come in later when I'm going to talk about the space-time resonances. It's not relevant if we just think in terms of the decay, the dispersion, the decay that comes from this dispersion relation. Okay, so on one hand, we have this problem that we have slower than 1 over t decay. On the other hand, now we had the same thing for the gravity waterways in 2D, so you could say that that's we are able to deal with. On the other hand, this gets coupled with the fact that in our case, we have a full set of quadratic resonances. What made it work, what we were able to do in the gravity case, the one that I described yesterday, is that even though there was this slower decay, there were no resonances. So morally, the equation, we can integrate by parts once and get 2 factors. So each one of them was kind of like square root of t, but once we integrated by parts once, we would get a quartic expression, and that we could estimate eventually. So that's that was all based on the fact that there were no resonances. The fact that the small denominators, which have been what we call the modulation function, which is the contribution of the waves going in different directions, that was the modulation function was different from 0. So there were no small denominators. So we could divide by it. Now, in our case, that's exactly what is this combination of problems that makes the problem much harder, which is that there are codimension 1 sets of quadratic resonances, and there are no matching null structures. I drew here one set of quadratic resonances. If we take the resonance set, so we are looking, the resonance set corresponds to the set of points where this function phi, the modulation function, which is lambda of c minus lambda of eta, could have been plus minus lambda of c minus eta. And so the resonance set corresponds to the place where this vanishes. And I drew here what the resonance set is for c is equal to 0. It's kind of an ellipse like that. It's all regular. There's no problem. It's all regular, but it's not an empty set. So you do have essentially a full codimension 1 set of quadratic resonances. And here the second graph basically, so the second graph shows how this resonance set, so it will intersect, it also intersects, so this resonance, so this blue line here is the resonance set, and it intersects so it intersects the set of points that come from this slow decay, which is c minus eta being close to the frequency gamma node which I had on the previous slide. So basically, the picture that we have is we have a full. Essentially, we have weaker decay than what we need, and we have a full set of resonances. That means that we cannot divide by the denominator. We have small denominators, so we cannot do a normal form to close the energy estimate. So what do we do then? And that's there's one redeeming feature for this in the algebra of the problem, which I want to get to next. So let me recall. So after this discussion of resonance, let me recall what you're looking at. So you're looking at the energy, the increment of the energy, En of t minus En of 0, and you had I integrate the d by dt of the n. So you have integral from 0 to t, and you have this expression. M was a specific multiplier that was not losing derivatives. That was not an issue there. M was a specific multiplier. And now, how do we estimate this kind of this type of space-time integral? Well, we move to profiles. So we write u of t is e to the it lambda capital U, w of t is e to the it lambda capital W. And then we write this expression in terms of profiles, just like what we did yesterday. So we have e to the I as phi. So this is the phi that comes in when we put the various. So when we put this capital W, we put the combination of the lambda. So we have this e to the I times the phi, e to the I as phi, and then we have this contribution of the functions, and phi, like I said, so it's a sum. Phi could be taken over the plus minus. So each one of these terms they come up. Well, actually, the ones from lambda for lambda of c and lambda of eta, one of them comes with plus, one of them comes with minus because you already had them here. Now they come from the term from the real part of u comes with the either side because it comes from the real part. Okay, so this is the expression that you are looking at. Now, to understand, we'd like to use we like to decompose them dyadically. Now, the profiles will satisfy equations, kind of like transport equations. The form dtu is some kind of expression, quadratic expression in u and u, and dtw is another quadratic expression in u and w. And this star here, this product here, it's just so it's an abstract kind of product just to show that you have products of objects of this type. So look at these bulks. So you have to understand all of these bulks, and we decompose them. We decompose them over 3 parameters. So the time. So the time. Keep in mind the time has to be we want to extend this for long times. So the time is going to be of the size 2 to dm. So we have the time is going to be of the size 2 dm. The frequency, the primary frequency that comes in, the frequency of the w's is 2 to the k, and the modulation, which is the size of this phi, is going to be of the order of 2 to the p. So it further decomposes the modulation in thinner and thinner pieces around the resonance set. And then this is all copied. This all copied as before. I'm going to focus on the hardest case, which is when we also restrict the frequency c minus theta to be near the stationary point, because that was the one that was leading to slower decay. Away from the stationary point, we could in principle have had better decay and we wouldn't have needed to do all of this. So I'm going to think that that c minus theta is basically around this. So c minus theta is basically around this stationary point, and then we have we restrict the size of the modulation, and we restrict the size of the frequency, and restrict the size of the time. And we have two options. So looking at an interval of this type, we have two options. We either integrate by parts in time, so in s, or we don't. And then the issue is when do you, for what kind of parameters do we use each option? So another way to write this term. So these are the terms, and then you have to take the sum over the k, the m's, and the p's. Now let's not worry about the sum, because once we estimate one of them, once we estimate one of them, we're going to be able to take the sum. So we look at one of these terms. And another way to write this term is to take d by ds, so to take d by ds of this so to integrate by parts in time, to use normal forms. And then what we do is we pick up the denominator, because we have to integrate e to the is phi, so we pick up the denominator, which is going to be of the size 2 to the p. And but the advantage is that we take d by ds of these profiles, which ultimately makes them quadratic. And now the difficulty is when p is small, because in some sense that was so far we haven't done anything. That was the whole issue with the fact that there is a full resonance set. That's why you cannot do this all the time. So the question is, what do we do for p small? Now for p small, so means that we are very close to the resonance set. For p small, we don't want to integrate by parts in time. And what we use is the key. So the key extra ingredient we have here is an L2 lemma on a degenerate Fourier integral operator. So this is the critical gain, and this depends on this function capital phi satisfying what we call a restricted non-degeneracy condition. So it's going to be a non-degeneracy condition that it's written on the next slide. So the L2 lemma, the main L2 lemma says the following. So if p, there's a certain range of p's, there's a certain range of how far we are from the resonance set when we want to apply it. So we say that if p is in a certain range, they think that p is really as small as it can be according to these restrictions. And then the operator that we are looking at the operator we had before. So looking at e to the is phi, then we restrict the function phi to being smaller than 2 to the p. And then here we have some kind of symbols. So we restrict the function f to be of size of frequency 2 to the k. We restrict the c minus theta to be close to gamma naught. And we apply this to a function f. Now at the highest order of derivatives, all we know about the function f is in L2, and we need to get an L2 bound. And we get the L2 bound that the L2 norm of this TP is controlled by a little loss, and then the point is to get these factors here. So we get these factors here, which are allowed. So we afterwards we are going to apply this for certain values of p, and it turns out that for the right values of p, like when p is very small, p is almost minus m, these factors allow us to so think of the last case here. So it's when it's p minus k over 2 is minus m, or if it's more like minus 2/3 m, then p minus k over 2 times 3/2. So let's say p minus k over 2 was minus 2/3 m, then p minus 2 p minus k over 2 times 3 halves, that would be 2 to the minus m. We also have to integrate in time, so we lose a 2 to the m. So this will be applicable for p is really close to minus m up to p minus k over 2 really close to minus m up to minus 2m over 3. So when p minus k over 2 is minus 2m over 3, these two terms are equal, and that's when we apply this lemma. Okay, so this is the Fourier analysis lemma. It's this is separate. If you want a Fourier analysis lemma, and it depends. What we are looking at here, just to give a brief idea of what how this works. So what we are looking at here, you're looking at the Fourier integral operator. So we have a Fourier integral operator with this phase phi, psi, and eta, and we apply it to a certain function f that depends on eta. But you also have to restrict to the function phi being close to so the function phi being smaller than 2 to the p. And in order for this to work, now when you work with Fourier integral operators, the favorable case is when the Hessian, the mixed Hessian of the phase phi is different from 0. So in this case, is d2 phi xi eta. This is the favorable case. Like for example, if you are thinking of the function phi is xi dot eta, the one that comes in the Fourier transform, that's what would happen. The mixed phase would be different from 0. Now, in our case, because you also have to restrict to this very thin neighborhood of the resonance set, there's not the right condition. The right condition is that this Hessian of the function phi, but apply to these vectors that are tangent, because these are vectors. So this grad c perp and grad eta perp, these are the vectors that are tangent to the resonance set. That object has to be different from 0. This is a scalar now. So this is a matrix, a 2 by 2 matrix, and this is a scalar. So it's that one, that component has to be different from 0. That's the relevant one because you can only integrate by parts. We can only integrate along the surface. You cannot integrate normal to the surface because we have this cutoff that's very thin. And so we have to verify that in our case for our function phi, which is this contribution of lambda, we get that phi is different, that this coefficient is different from 0 when phi vanishes. Okay, so that's so this is the L2 lemma. It's a separate, it's kind of a separate, all right, so as I said here, this can be used to control the contribution of the small modulation, p minus k over 2 being close to minus m, in fact, up all the way up to minus 2m over 3. And now for the higher modulation, so this lemma we use for the small modulation. Now the proof of the lemma is basically a TT star argument. This is always to prove this kind of Fourier integral operator. If we are looking on L2 bounds for a Fourier integral operator, that's some technique that's very common in Fourier analysis. Of course, you need to understand the oscillation of the phase because everything depends on the fact there was oscillation in the phase. And there's a the so-called TT star argument lets you use this oscillation. So that's how we prove this. We basically look at the TT star, and then we are able to understand the size of the kernel of the TT star operator, and then we are able to prove these bounds that we want. So this will allow us to use, as I explained here, because this factor is basically not worse than 2 to the minus m, this will allow us to go to look at the small modulation almost up to p minus k over 2 up to the minus m over minus 2 to the minus so p minus k over 2 smaller than minus 2m over 3. Now, in the case of the higher modulation, we have to use the other formula. So we have to integrate by parts in time. Now, when we integrate by parts in time, there's one more algebraic invariant that we need, namely that when we integrate by parts in time, we are going to lose a derivative because there's this dtw, and there was an extra derivative in front here. So this will lose a derivative, but thankfully this is compensated by exactly the depletion factor that I mentioned earlier, because the model that you're looking at is this exact L2 conservation. The multiplier that comes in, the cubic energy in the energy estimate had this kind of formula, and this fact that c minus eta times c plus eta turns out to gain one derivative when resonance function was small. So the key algebraic point that I wanted to say is that if the phi is small, then so if the resonance function is smaller than 1, then this multiplier m of c minus theta gains a derivative. It gains a derivative from the fact c minus theta dot c plus theta. This doesn't have the c minus theta has size 1, c plus theta has size 2 to the k, but the vectors are almost perpendicular when we are when we are close to the resonance set. So this is the algebraic part this is the algebraic correlation that lets us deal with the case of higher modulations. Okay, so that's so this is basically this is how we prove the energy estimates. Now it turns out that they found a very similar structure, the same algebraic correlation for another model, what is called the Euler-Maxwell system for electrons, which is a plasma model. It's also a 2D problem, and it had almost the same kind of features that one doesn't have enough. On one hand, one has a full set of resonance. On the other hand, one doesn't have enough decay of the evolution so one has to do normal forms. And it turns out that this structure, my feeling is it's a kind of in Hamiltonian systems like that. There's some algebraic correlation of this type that we're able to use. And these energy estimates, the conclusion that we have is that these energy estimates can be used to control the growth of all the high order weighted norms. So the energy weighted norm. So we use these energy estimates, like I showed here, we used to control the Sobolev norm of U. And one can also do almost the same thing, applying the vector fields omega, so the rotation vector fields, to control the energy of the vector fields applied to the solution. So this is the part of the energy estimates. If you compare what I was talking last time, there's the new issue, namely that on one hand the decay is not strong enough. On the other hand, there's a full set of resonances. When I was talking about the 2D gravity system, there were no resonance, so you could just divide by the phase and we could gain an extra factor in the right hand side. Here we have this extra issue, and so it's compensated through this L2 lemma that allows us to still gain something in the case when we are close to the resonance set. Okay, so this is basically the last slide I had on energy estimates. Maybe I should stop now for a couple of minutes if there are questions.